Hello everyone. In this video we're going to be discussing section 3.8, use inverse matrices to solve linear systems. So this officially is our fifth way to solve linear systems. We've got graphing, we've got substitution, elimination, Cramer's rule, and now inverse matrices. So let's get into it. The n by n identity matrix is a matrix with ones on the main diagonal and zeros everywhere else. So going from top left all the way to bottom right, you can see these ones, and then I have zeros everywhere else. That is called the identity. The reason why it's called the identity is because if I take it multiplied by any matrix, that matrix is going to remain the same, whether it's on the right or whether it is on the left, because remember, left and right multiplication here, we discovered that the commutative property doesn't always hold. Alright, so it does hold in the case of the identity, however. Okay, so identity for 2 by 2 and a 3 by 3, one's on the diagonal, zeros everywhere else. Okay, two n by n matrices A and B are inverses if their product ends up equaling the identity. Alright, and that was similar to the idea of inverses with real numbers. So I have 7 times 1/7, that would equal 1. Those were considered inverses. Right, and it's going to be the same idea as far as matrices are concerned. Alright, so the multiplicative inverse there, I would end up equaling 1. Here I end up equaling the identity. So I can either multiply them like AB or BA. Either case, if I get I, they are inverse matrices. Okay, one way to determine if a matrix even has an inverse is to find the determinant of A. If the determinant is not equal to 0, then it has an inverse. If the determinant does equal 0, then I cannot find the inverse. So the symbols for an inverse is, it looks like an A to the negative first power, but that is just read A inverse. That is read A inverse. Okay, here is the formula to find an inverse for a 2 by 2. So I am going to have 1 over the determinant of A, 1 over the determinant of A, or you can use our formula that we remember from 3.7, AD minus BC. And I've got some black magic that happens with the original matrix. So if my original matrix is ABCD, I go ahead and swap the diagonal for D and A. D and A swap positions, and then I negate B and C. So if I can remember the determinant of A is equal to AD minus BC, alright, I can kind of use this to remember how to rearrange this matrix. Alright, I want to swap A and D, and then I want to make B and C both negative, but I want to keep them where they're at. Alright, that's how I kind of remember it. It kind of goes with the determinant formula. And that does say provided that the determinant is not equal to 0. So it's going to be easiest if we look at an example. So let's look at example 1. Find the inverse of A. Alright, so first and foremost, I want to write A inverse. A inverse is equal to 1 over, I've got to find my determinant here. That's 3 times 5, or 15, minus 2 times 8. 2 times 8. And then I need to jumble up my matrix. Alright, so going through that process again, I'm going to swap 5 and 3. So 5 ends up in the top left, 3 ends up in the bottom right, and then I'm going to negate negative 8 and make that a negative 2. Alright, so I'm going to go through the multiplication and subtraction process here. I have 15 minus 16, which is just 1 over negative 1, which is just a negative 1 that I'll be distributing. Okay, so that's still times the 5, -8, -2, 3, 5, -8, -2, 3. And so finally I'm going to distribute that -1 into my matrix here. So my final answer should be -5, +8, +2, and a -3. That is A inverse. Right, and double checking how they work everything out. They have it nicely written out, and we were correct. We can confirm for the record. No harm in confirming here. If I have A, here's A, and I've got A inverse, I should be able to multiply them and get my identity. Alright, so I'll just scoop and pour. Scoop and pour. That gives me -15 plus 16. Alright, that looks good. That's going to be 1. Alright, and then I've got 3 times 8, that's 24, and that's -24. That gives me 0. So that's 1, that's a 0. Scoop and pour. That is -10 plus 10, which is a 0. Alright, good. And then, last but certainly not least, 16 minus 15, which is a +1 again. Alright, so I end up with the identity. That's good. Alright, so find the inverse of the matrix. Feel free to go ahead, pause the video, and see what you get. If you get fractions, decimals, that's alright. Just make sure that if it's an ugly decimal, don't round. Do not round. Press your fraction to decimal button or math enter and get a fraction for me. So pause the video, see if you can get the inverse. Alright, the inverse is a whole bunch of 11ths here. It's 2 11ths, -1 22nd, -1 11th, and 3 11ths. Alright, let's see if you can get the second one. And the third example. Alright, so on to the process of actually using an inverse to solve a system. So you will have one problem like this on your test. So it's important to get the process down. Alright, so all of my systems are kind of written in this form. A times x is equal to b. So I have my coefficient matrix A, and that's multiplied by my variables. Alright, so let's go ahead and just show you a mini example. Alright, here is my matrix, and then I actually have that capital X matrix. Those are my variables, and those are set equal to my constants here if I'm putting it in standard form. Alright, so if you scoop and pour, this is going to give you 2x plus y equals 1. And then scoop and pour this, that gives you 3x plus 4y equals -1. Alright, so that's what our system ends up looking like, just to let you know. So they're all in this form. I just wanted to show you what it looks like. Alright, x is the matrix of variables, and b is the matrix of constants. So I want to go ahead and make sure that I have everything written correctly. Step 2 says find the inverse of matrix A. Now what I can do is if I have A times x equals b, and I multiply both sides on the left by A inverse, so this gives me A inverse b, these two together equal the identity. So that gives me the identity times my variable. And the identity times anything is going to be itself. So x just equals A inverse b. But it has to be in that order with A inverse on the left. Right, so that's really all we're going to do is we're going to find the inverse of A, multiply it on the left by b, my matrix of constants, and that's going to give me x. Alright, so here I have my equation, which would end up looking like 2x minus 7y, yada yada. Alright, and it is set equal to my constant matrix. Alright, so first step, after we write it in this form, we want to go ahead and find A inverse. Alright, so I need to find 1 over the determinant of A, and then I need to jumble A to get it in that form. So once I actually work my magic out in front and distribute that number, I get A inverse to equal 4, 7, 1, 2. So there is A inverse. That is A inverse. So then I'm going to multiply that on the left by B. So I need to scoop and pour. Scoop and pour. Keep in mind that these are going to cancel out here. Alright, those are going to give me the identity if you found the correct A inverse. Alright, so X, my coefficient matrix, ends up equaling 0, -2, 3, -1. Alright, so here I want you to go ahead and solve this 2 by 2. Alright, so you should end up resulting in an X that is equal to a 2 by 2. So find A inverse and then multiply it on the left by B and see what you get. Alright, hopefully you guys got -1, -2, 4, and 1. Be sure to check out the problems and the different dimensions and everything. So depending on the dimensions, you could be solving for 2 variables or 4 variables, something like that. If you guys have any questions, feel free to send me an email and ask, and I wish you guys the best of luck. I'll see you when I see you.